Welcome back everyone. In this video, we can discuss about various logic gates in detail. So the logic gates are the basic building blocks of any digital system. It is an electronic circuit having one or more than one input and only one output. So note this point, a logic circuit or logic gate is an electronic circuit. We can apply one or more than one input to it and it generate only one output. The relation between the input and output is based on certain logic. By changing the logic, we have different logic gates like AND gate, OR gate, NOT gate, NAND gate, NOR gate, XOR gate and XNOR gates. These are the commonly available logic gates. Among these, AND, OR and NOT form the basic logic gates. Using these or combining this, we can generate the remaining gates like NAND, NOR, XOR, XNOR. All these gates are available common. Okay, and combining these gates together and we can generate various digital logic or we can generate different digital circuits. So we can discuss each of these gates in detail and start with the AND gate here. So AND gate is a logic gate. It can have n number of input and only one output. And the value for this n is here n greater than equal to 2. Means for an AND gate we require minimum of 2 inputs and it generates a single output. And the AND gate operation is represented like this: A and B and C means 2 input AND gate. It generates a single output which is represented by this Y variable here. In another way, we can represent the AND gate operation A dot B dot C. 3 input AND operation and generate a single output. In another way, we can represent the same logic like this. Simply ABC. Indicate an AND operation between A, B and C input and generate a single output. Okay. So, the logic diagram of this AND gate is this one. This is the symbol or the logic diagram representing AND operation. This is a 2 input AND gate and generate a single output. And for this 2 input AND gate, the truth table is like this. This truth table actually indicate the operation of this AND gate. If 2 input A and B, if both are of value 0, then the output must be 0. Output is always 0 if both the inputs A and B are of value 0. And if B is 1 and A is 0, this case also the output is 0. Again 1 0 combination, again output is 0 and for 1 1, then it generate an output with value 1. From this truth table, it is clear that an AND gate generate an output 1 if both the input comes with value 1. The 1 and 0 actually means 0 indicate the switch is off. The switch is in off stage. And 1 means the switch is in on stage. Okay, so if both the switches are in on stage, then only this AND gate generate output. Otherwise, the values remains 0. That means the output remains in switch off stage. Okay, so consider the simulation for this AND gate. Okay, so this is the simulation of our AND gate. 2 input AND gate. Okay, and the first input is represented as A, second is B with output Y. So consider this. First case, both A and B input with value 0. Okay, value 0 for the input actually indicate switch off stage and value 1 indicate the switch on stage. Okay, if A is with value 0, the first case, B with value 0. In this case, output remains in off stage. Okay, now we can make this case. A with value 0, B with value 1. Means A is in off stage, B in on stage. A is in off stage. Now we can switch on this input B. So, flow starts through this second input and still the output remains 0, or in the output remains in switch off stage in case of this logic gate AND. And the second case, A input is 1, means A is on, B is off. So we can make this B off now and we can switch on this A input. Still the output remains off in case of this logic AND gate. Right? Next is A and B with value 1. Means we need to switch on both the input. In this case, the output become on. That is, both if A equal to 1 and B equal to 1, output is 1. That is, output also comes in active stage. This is the simulation corresponding to the logic gate AND. So, note this point, if both the inputs are equal to 1, then only AND gate generate an output. Otherwise, it remains in switch off stage. Okay. So, next we can consider our next gate, that is the OR gate. OR gate is also like our AND gate. It has n input with n greater than equal to 2 and it generates only a single output. For an OR gate, we require a minimum of 2 inputs. Okay, and this OR gate operation is represented like this. A or B or C means this is a 3 input OR operation and generate a single output. And thus, this plus symbol also used for representing the OR gate operation. Okay, next is the logic diagram for this OR gate. The input connecting part is represented as a curved one. And this one indicates the output. Next is about the truth table corresponding to this OR operation. If input are of 0, 0, then output is 0. Then 0, 1, output 1, 1, 0, output 1, 1, 1, output 1. So from this it is clear that for an OR gate, if any of the input is in on stage, then the OR gate generate output. But in AND gate, in order to generate or switch on the output, what we want to make both the input in on stage. But in OR gate, in order to make output on, we need to make at least one of these input as switch on. Okay, so consider the simulation corresponding to this one. Okay, this one actually indicate a 2 input OR gate. And the logic diagram corresponding to this OR is this. Okay, so this is the first case. A with value 0, B with value 0 means both in switch off stage. So the output is also off in off stage. Now A with 0, B with 1 means we need to switch on the second input. Then a flow start from input to output and output become active. Next case, A is active, B is off. Like this. So, whatever value passed to this A input which is now available, which will now available here in output. Okay. So, next is both A and B in switch on stage like this. So, the output still in active. So, this is the simulation of our OR gate. For the OR gate to generate an active stage in its output, what we want to make, at least one of this input we want to make in an active or in a switch on stage. Okay. So next is about our NOT gate. Okay, NOT gate is also known as inverter. It has one input and it has one output. And the operation of this NOT gate is just the complementation. Whatever value input to it, it will generate it complemented form to the output. Okay, so we can represent the operation of NOT gate like this. Y equal to NOT of A. Means the complement of A input is available in output. In another way, we can represent this NOT gate operation A bar, complement of A input to output. In another way, using this single card, we can represent this complement operation or invert operation. The logic diagram corresponding to this NOT gate is this. The value provided here in this A input, its complemented form is available in output. If the value is equal to 1, then output is 0. If value equal to 0, then output become 1. Okay, the truth table corresponding to this NOT gate is this. Single input, single output gate. If it is 0, then output is 1. If it is 1 in output, if it is 1 in input, output is 0. So consider the simulation for this NOT gate now. Okay, so initially input, this is the NOT gate or inverter. If the input is 0, then output become 1. If here it is in off stage, then output become on. If it is on in input, output become off. So this is the simulation of our NOT gate. So all these gate OR, AND and NOT, these are the basic gates. Using these three, we can generate all other gates. Such a modification is our next logic gate, that is the NAND gate. Okay, NAND gate is not AND. A combination of NOT gate and AND gate is NAND gate. And this NAND gate also we need minimum 2 inputs and n may be any number. And it generate only single output. This is actually not of AND. Take the AND operation first, then its complemented form, which will form our final output of NAND gate. AND operation first, then NOT it or complement it. Okay, so the logic diagram is, this is the logic diagram of NAND gate and this is the meaning of our NAND gate. AND operation first and its output is inverted and generate the final result of NAND operation. And this is the logic diagram of NAND. And with a bubble here in this output part indicate AND operation first, then that result is complemented. Okay, so this is the truth table corresponding to this NAND operation. For this 0, 0, in case of AND operation, the output is 0. But in case of NAND operation, the output become the complement of our AND output. If it is 0 here, then it become 1. For 0, 1, AND result is 0. So its complemented form become the output of NAND for this particular combination of input. Next input combination is 1, 0. For this 1, 0, AND output is 0. And for NAND is complement of this AND result. 0 complement is 1. And for 1, 1, the AND result is 1. Its complemented form is 0, which is the final output of our NAND gate for the input sequence 1, 1. Okay, consider the simulation corresponding to this one. So look at here. So this is our AND logic and this is the NAND. What is the difference? Here in AND output, here we have a bubble. This bubble indicate inversion of AND output. Inversion of AND output indicate NAND operation. Okay, so this is the case. both the input switches are in off stage. So in this, AND generate 0 output, no output. So but here, if both the switches, input switches are in off stage, then output is 1. Just the reverse of our AND operation. Okay, now make this single output active here, single output active here. For an AND operation, if the single input active here, single input active. In case of AND operation, if the single input active, output becomes 0. Its complement, 0 complement is 1, which is available here in NAND operation. Next is activate this B. In case of AND operation, if a single input is active, output is 0. If it's 0 in NAND operation, NAND generate its complemented form in output. Okay, so in single input is active here, NAND generate F1. And if both are 0, still it generate an output. That is output a value, or this output switch is in on stage now. Now consider a case. If both the input are in active for an AND gate, output become active. But here in NAND gate, the output is the complemented form of AND. If both the switches are in active, output become 0 or in switch off stage now. Okay, so just the complement of AND, that is NAND. Negation of AND operation, that is NAND. Okay, so this is about NAND logic. Okay, and next is the NOR gate. Exactly like our NAND operation, NOR is not of OR gate. Not of OR operation is NOR. And it also have more than or equal to 2 number of inputs and generate a single output. And we can represent this NOR operation like this. OR first, then the result is complemented. The complement is represented using this over bar. Okay, the logic diagram corresponding to this NOR gate is this. OR gate with a bubble. This bubble indicate first perform the OR operation, its result is complemented, which form the output of our NOR gate. And this indicates the meaning of our NOR gate. OR operation, its output is complemented and form the final output of our NOR gate. Right? So, this is the truth table. Truth table means complement of OR output. If for input 0, 0 or generate a 0 as the output, right? And in case of NOR, this 0's complement is available in NOR. That is, here it is 0, so its complemented form is available as an output for NOR gate with input sequence 0, 0. And for 0, 1 or output is 1, its complemented form 0 is available here. And for 1, 0, the OR operation generate an output 1. Its complemented form is available here. And 1, 1, the OR gate generate an output 1. Its complemented form, that is 0, is available here. Okay. Now we can check the simulation corresponding to this NOR gate. So this is the OR gate and this is the NOR gate. In the logic diagram, the only one difference is in NOR gate, we need a bubble at this end, at this output side. And here we have no bubble. The bubble indicate first perform the OR operation and result is complemented. Okay, so if both the switches are in off stage, output is 0 for OR gate. And its complement happen in NOR gate. That is, both the switches are in off stage, then output become active. So if one of the input is active, then OR gate generate an output like this. And here one of the input is active, then its complemented form become the output of our NOR gate. That is, the output is in off stage now. Okay. Next, switch of A and switch of B. In case of OR gate, it generates an output through this circuit. But here, it generates no output. Just the reverse takes place in NOR gate. Okay. If both the switches are in on, then OR gate generate an output. If both the switches are in on stage, then the NOR gate generate no output. Okay. And if both the switches are in off stage, then OR gate generate no output. But here, if both the switches are in off stage, then NOR gate generate an output. So this is the simulation of our NOR gate. Now we have two more special gates, that is XOR and XNOR gate. So this XOR gate is XOR. This is the abbreviated form of exclusive OR. This exclusive OR gate is represented as EXOR gate or XOR gate, which also require n number of input with n greater than or equal to 2 and it generates a single output. Okay, and this operation is represented like this, A XOR B, and the operator representing this XOR operation is this. Okay, and the meaning of this XOR operation is this. A XOR B means AND between A input and B complement. Then OR, the result is OR with A complement and B. Okay, so this is the meaning of our XOR logic gate. So always remember this expression. A XOR B means A input value is AND with the complemented form of B input. Similarly, A complemented form is AND with the input value B. Then perform an OR operation between these two results. So, this OR operation generate the result of our XOR gate. So, keep this expression in your mind always. Okay, so this is the logic diagram of our XOR gate. OR gate with an extra curve here, an extra arc here in the input side. Okay, the truth table is this. AB with A XOR B as the output. So for the input 0 0 output is 0 0 1 1 1 0 1 1 1 0. For understanding this truth table well, we need to consider this expression again. A XOR B means A B bar plus A bar B. Suppose the input combination 0 0, A with 0, B with 0. Then for apply this value to this expression, then it become A is 0, B complement is 1. 0 and 1 plus 1 and 0 is 0. This 0 is generated as output of our XOR operation. Next input combination A with 0, B with 1. Here A with 0, 0 and B complement. B is 1, so its complement is 0. Plus A complement is 1 and B. So 0 plus 1 is plus means OR operation. 0 or 1 is 1. Again in A equal to 1, B equal to 0, 1 or 0 is 1. And A equal to 1, B equal to 1, here again it generates 0. So from the truth table of XOR gate, it is clear that XOR gate generate an output equal to 1 if only one of this A and B input become active. If both equal to 0 and both equal to 1, then A XOR B generate 0 as the output. Either A equal to 1 or B equal to 1, then it generate an output equal to 1. Now consider the simulation of this XOR gate. Okay, this one. XOR logic diagram is OR gate with an extra arc towards the input side. Now both A and B input is 0 or in switch off stage, then the output is 0. If one of the input is switch on, then as then current flow through the circuit and generate an output. Okay, again A is switch off and B is switched on. Then again here form a connection and current flow through the circuit and generate an output. And next case, both the inputs are in switch on stage. So in this case, based on this, it generate no output. Okay, so this is the simulation of our XOR gate. So from this it is clear that if either A or B is equal to 1, then only XOR generate an output equal to 1. In the other two cases, that is if both A and B equal to 0 or both A and B equal to 1, in these two cases XOR generate 0 as the output. Next case, a special gate like XOR, that is the XNOR gate. This is exclusive NOR gate. XOR is exclusive OR gate. XNOR is exclusive NOR. Exclusive NOR can be abbreviated as XNOR. Okay, it also required minimum 2 inputs. Okay, and it generate single output. And the operation corresponding to this XNOR gate is like this. A complement and B complement, or A and B. First AND between the two input A and B. Then A and B input is ANDed together without any complementation. Then the generated results are ORed together and generate the final result of XNOR gate. So this is the logic diagram corresponding to XNOR. XOR with a bubble at the output side. That is the XNOR gate. Next is the truth table. How to get the output in this truth table? For that, we need to follow this particular expression of XNOR. A complement B complement plus AB. Means AND operation between complement of A and B. Then AND operation between A input and B input. Then these two intermediate results get ORed together. So it generates the final result, which is the result of XNOR gate. For the 0, 0, while applying this input value to this expression, here it is 0 complement 1, 0 complement 1. That is 1 and 1 plus 0 and 0. So the final result is 1. Here 1 and 0 plus 0 and 1, 0. Here 0 and 1 plus 1 and 0, 0. If A and B both are equal to 1, then 0 and 0 plus 1 and 1 equal to 1. So this is the output of our different input combination. Consider the simulation. Okay. So for this is the logic diagram corresponding to XNOR. An OR gate with an extra curve is actually XOR. For that XOR, we need to put a bubble here at the output side. Now it forms the XNOR gate, the logic diagram of XNOR. If both the input equal to 0, then it generate an output equal to 1. And if any one of the input is equal to 1, then it generate no output. Similarly, A equal to 0, B equal to 1. Then also it generate no output. If both the input equal to 1, then it generate again an output. So this is the truth table of our XNOR gate. Means if both the input are equal, then only it generate an output. If both are equal to 0, then output is 1. If both are equal to 1, then it generate 1 as an output. But in case of XOR, if both are equal, then it generates 0. And if A equal to 1, B equal to 0, or B equal to 1 and A equal to 0, in that case, XOR generate 1. So just the reverse of XOR is XNOR. And this is the simulation corresponding to our XNOR gates. Okay. So among these set of gates, OR, AND, and NOT gate. These three form basic gates. Using these gates, we can combine these gates together and generate some special gates like NAND, NOR, XOR, XNOR. Okay, so all these are about logic gates. Combining these logic gates together, we can generate different circuits. Especially like this, XOR and XNOR gates are used for implementing full adder circuit, half adder circuit, subtractor circuit, and all. Okay, we can discuss all about these complicated circuits in our coming video. Thank you.